She told us to add the negatives.
Yeah, that works. Okay, so we'll call this methods for solving. I put polynomials, even though that looks like a D. I lied. I mean inequalities. That's what we're doing. Okay. And while it is an inequality, there's a polynomial is a piece of it, but I should get the right title here. So we have an inequality because we're looking at this. This usually replaces an equal sign. This is a less than and equal to. You can also have less than signs, greater than signs, and greater than and equal to. All potential options for us, right? It works for most of the part algebraically the same as a equal sign, except if you were multiplying or dividing by a negative, then you end up flipping the sign. Otherwise, mostly this is the same. It's just that the type of answers we get, when we're solving for a polynomial, we might get 1, 2, 3 integers as answers. When you're looking for inequalities, usually you're getting almost infinite amounts of answers. It's essentially big, large ranges. Something in my throat, sorry. So what we'll do first is we're going to set, not quite equal, but we're going to make sure that the 0 is on one side of the equation. So for this one, that's relatively simple. We're going to move negative 21 to the left side of the equation. So here's our left side. Here's our right side. We'll move it over, and it becomes plus 21. And we get is less than and equal to 0. Okay. This one happens to be a quadratic. I take a look at this power. This is the power of the leading variable here. There's some quick ways to solve quadratics. It just so happens this one has to have a coefficient of the leading variable of 1. So there's this really fast trick to factoring. You're ended up just looking for two numbers that add to the middle, which happens to be negative 10, or the b value, we could say. And those same two numbers are going to multiply to, technically it should be a times c, but because this is 1, it doesn't change it, so they usually just say the c value, and in this case that's 21, or the c value, okay? There's actually so many answers for the adding and subtracting, so it actually makes more sense to work on the factoring, or the factors of 21. So 1 and 21 work, but I don't think I'll get a value of negative 10 when I add. 3 and 7, for sure something's going to work there. 3 and 7 work, but we need negative 10. So if they're both negative, we get both of them. So what that means is the second value in each of the brackets is just a negative number. And then we just put an x in the first value of each, and we have it. We have a factored version of this. Sorry about this.
It's okay, no problem.
So, what's the purpose of this? What's nice about this is we found zeros. Now, if it was an equal sign, this is almost like the end of it. We're trying to find values that equal 0. But in this case, we're looking for some kind of change graphically. So you have a couple different methods. One of them, I believe, you use a number line for solving an inequality. Another one, you use a chart, I believe, right? Charting. And then finally, there's a graphical version. We'll maybe tackle that one last. So what we're going to show here is we're going to draw a number line out, and we need to put some key points. Some of the key points are the same way we would normally solve an equality, something that's equal, or a polynomial. We're going to find out what these 0 values are. So in this case, we're looking for, because we have that equal sign there, think of two numbers, we're looking for x. Oops, I didn't need the bracket there. X minus 7 is equal to 0, we'll say, and x minus 3 is equal to 0. Now, the reason I didn't put, let's see if I can move this down. Yeah, I can. The reason I didn't put the greater than and less than sign is because we're going to use the number line to actually figure out that piece, okay? We'll explain it in a minute. Here we end up with x at 7 and x at 3. So we have two key points here. Let's say we'll try to go from left to right. We have 3 and we have 7. What I actually want to do is I want to define the end of this number line also. So the ends of the number line, to the left, it goes on to negative infinity, and to the right, it goes on to infinity. So what we've now done is we've broken this into sections, okay? One of our sections is from 3 below. The other section is between 3 and 7, and the other section is above 7 to an infinite number of answers. And we're going to use this to try to figure out what our answer is. We do have to be able to read this inequality here. This one happens to be, when we go like this is less than and equal to, okay? So we know the equal to part, it does equal 3 and it does equal 7. So it is going to be, and sometimes you use different signs. Usually on a number line, they'll fill that in with a solid circle here, okay? If it happened to be just a less than or equal, they'd sometimes use like a hollow circle, meaning it doesn't quite touch that number, but everything around it does. We'll take those away for now. And what we're gonna do is we're actually just gonna pick values in these ranges. So we'll start with this one. This one's probably the easiest range to understand. I'm looking for numbers between 3 and 7. 5 is a nice one. 5 works out well. And what we do is we can take that exact inequality. We have x minus 7 and x minus 3. And what we're going to do is we're going to figure out if it is a less than and equal to 0 as part of this. So we're going to take that value of 5 and we're going to plug it in for the x value. Okay. Now, normally they'll start to show this by just using like plus and minuses, but I'll go through the whole process and then I'll talk about how we can speed it up. We plug in 5 for x. Okay. So just like as if we were trying to find like maybe a y-intercept, something like that. And then we're going to carry out this little algebra here. 5 minus 7 gives us negative 2. 5 minus 3 gives us positive 2. So we end up with negative 4 is less than 0. And what we do is we have to check this. Is this true? Is negative 4 less than 0? Yes, that is. That's true for us. So what that means is this is one of our ranges. This is our range. From here to here is true. We just took one number in the range, but as long as one of them happens to work, we're okay. As long as we've carried out our other algebra correctly. We'll go and test the other ones just to make sure, and then we'll talk about kind of a shortcut they use with pluses and minuses, which is going to actually lead us into the charting. Oh, I used the wrong thing there. Something less than 3 but greater than negative infinity. Yeah, it's just anything less than 3. 0 is a nice number. It's usually pretty easy to work with. 1 would also be great. So we can plug it in. We're going to go with 0. I'll draw it in here twice. Minus 7. And then 0 minus 3 less than and equal to 0. Okay, that becomes negative 7 times negative 3. Turns out that's negative 21, not negative. As soon as I said it out loud, I go, that can't be right. A negative times a negative is positive, so we get positive 21 less than 0. Is positive 21 less than 0?
No.
This is not true, okay? So in other words, this is not part of the range, okay? This part here is not part of the range, okay? So we don't include that as a potential answer. And then we got to check the other value. I mean, 10's really nice. 10's a pretty simple one to work with too. Exact same concept. So what we're doing is we're getting used to plugging in these values into our factored form. The factored form is nice because it gives us some shortcuts to it. Let's minus 7, there you go, and minus 3 less than and equal to 0. This gives us 3 and 7. Very obviously now we get positive 21, and we've literally already checked that one. Positive 21, not true. Okay, so we went through the process of checking. So what we discovered is our answer to this question is this range here. Okay, it is all the values. You could say the answer to this is x is the element, if you were to write it like this, almost like a domain. You could say x is the element of all numbers such that for it to be below, so actually we won't write that way, that's more of a domain. Let's write it this way. We're just going to say for our answer, x is less than and equal to 7, okay, and greater than and equal to 3 as our set of answers here. Sometimes they'll write it like this. Because it's equal to, you'll use a set of square brackets. They'll do like 3 and 7. Have they ever done that?
That's what.
Perfect. They use this, and what have they done? They've said x is an element of these. Great. They'll use that little notation as part of it. Had it been, and I have solid circles here because it's technically a part of it. It's touching those values. Had it been just greater than and less than, I would have put like hollow circles, and I would have used these brackets instead. More of a circular curved bracket to represent that it's less than or equal, but, sorry, it's less than or greater than, not the equals to, okay? So that's a number line version. Another way to check something like this out is to build a chart, which to me I think is actually personally pretty close to this. I think what they'll usually do for your chart is your first column here is your two sets of brackets. You have x minus 7 and x minus 3. How you guys set it up? Awesome. And then they'll do f at x. And what that represents is what is your equation equal to. So we're actually going to be doing a bunch of multiplication. And you're going to do exact same idea. This one just looks a little different. We're going to work with this exact same range. So solving this range is also important. How we had to figure out there's 3 and 7, and we have to get their end and beginning range. They'll probably say something like this, negative infinity, so they'll give us a range, and let's say 3 squared. Do they give you the square? Yes, they do. Great. Let me move this over a bit. That's our first range to the left, so we're just representing it using some notation. The next one here will be 3. Oops. The next one here will be, I'm using the wrong thing. There you go. 3 and 7. That was our middle range. And we already know our answer, but what we're going to do is we're going to just essentially go through the same process using a different method. And then finally we have 7 and infinity. Notice with the infinities I use a curved bracket. They do too? Good. Because you can never actually touch infinity. It's more of a concept, so you can never be equal to infinity. Okay, so just keep that for your notation piece. They call this a chart because we essentially have rows and columns to it. And the purpose of this, I made some of my columns far too long, is we're really trying to figure out with some values if you're negative or positive in these areas. So first idea here, what they want to know is if you put in a number in here, so just like we did before, we took the number 0. Here we go. If we take the number 0, which is in that range, if I plug 0 into this piece, do I end up with a positive value or a negative value? Well, 0 minus 7 is a negative, okay? If I put 0 into this one here, what would we end up? 0 minus 3, we get a negative number. So now what you do is I think, what is a negative times a negative? And if from that, I solve that it is a positive. What that's telling us is it is positive, must be greater than 0. And therefore, this can't be part of our range. Okay, so this little part here is our answer. This is always what we're trying to do. And the argument could be made that you can do the same concept with a number line. They've just organized it nicely in a chart. We'll use our same value, 5 again. 5, if we plug 5 in here, this actually becomes a negative. But here we get a positive, okay? Negative times a positive, that gives us a negative. Hey, that checks out. Negatives are less than 0. So that means we are less than and equal to 0 in this range here. And then finally, we check out the last piece. We took the number 10. Does it work out nicely? 10 gives me a positive. 10, if I plug in here, gives me a positive, and a positive times a positive is a positive. Hey, this column did not work out. These two don't. This one does. We have now just discovered our range. And that can be it. You go to write your answers, same concept as 4. X is an element of 3 and 7. Okay? Finally, graphing something like this is important. So, let's build a bit of a graph. When we find 3 and 7, we have essentially, do I have enough? 1, 2, 3. Oh, I do. Nice. 4, 5, 6, 7. Here we go. We have x-intercepts. Okay, we essentially have 2 x-intercepts. What we need to figure out is its behavior when we're going to graph this. So behavior around x. So we're looking at when something is going from negative infinity up to this value, and this value happens to be 3, between 3 and 7, and then finally towards positive infinity. So you might even put these on, that should be a negative infinity, on your number line here. This will be just a rough sketch, but it's of the exact same concept. If you're plugging in an x value, what does it become? So sometimes they'll use some very extreme values here. I'm going to rewrite our little bracket again. If you remember, it was x minus 7 and x minus 3. Yeah, greater than or equal to 0. Okay, what we can decide to do here is we can choose what we did before. We have some values. For instance, we started with 0. We plugged it in. And very quickly with 0, that chart's really nice. It told us we had a positive value. Positive just means you're above the x-axis. That's what positive values of f at x are. If it is a positive value, it's above. If it's below, that means your f at x is a negative value, okay? So if we take a look at our chart, we know that's the case. So we still have to do some of that algebra. We're just visually going to represent it with a graph instead, okay? We could, if I put in our negative infinity, positive infinity, it's going to eat up everything. We'll just use the values we used before. Same idea before. We could use 0, and we plug in zeros. We end up with 2 positive. So we know this graph does something like this until it gets to this point. Then we knew when we plugged in that value of 5, we ended up with a negative and a positive, which ended up being a negative value in the chart, okay? And what that means is that it's negative. It's below the y-axis. So it comes down. It comes back up to here. These points are anchors. We know that we're touching them. So we're just doing a general drawing of it. So we knew from here we were positive, so I must come down to here. It's possible I touch this and then go right back up and never cross over. But it turns out when we went to the next range, it went into the negatives. So I know I go down in the negatives. I must come back up to this piece. It's possible I go right back down again. We're just going to test and find out. And when we look at our chart, it turns out it became positive again. So it continued upwards, okay? Now, this is a very poorly drawn quadratic, but it is a quadratic. I see. This must have the form of a quadratic here, okay? And this will help when we're going to graph other polynomials, and that's why I kind of started with the word polynomial there, is because when we do other polynomials, you might get behaviors. Let's say we have multiple points. You may have something where it touches, goes back up, then crosses through, then goes back up again. Okay, and that's where the positive range for f at x and the negative range become very important.